Hello, I'm Dimitris Mavridis. I'm a statistician working in network meta-analysis. And for the next 1 hour and 15 minutes, I will try to give you a conceptual understanding of what network meta-analysis is. I'm not going to use many formulae or lots of Greek letters. And I'll try to describe you what it is, the benefits, and the limitations. I have borrowed many slides or many ideas from my slides from other people, from other presentations, so I would like to help Anna Haimani, Georgia Salanti, and Julian Higgins. There are some fancy slides. These are not mine. So actually, network meta-analysis is an extension of standard meta-analysis, what we understand by meta-analysis, to the case where you have more than 2 treatments. So before starting, at any point, feel free to interrupt me if you have any questions, or you need me, or you don't understand my accent or whatever. So I will start with standard meta-analysis. Suppose that we have 2 interventions that we want to compare the relative effectiveness between them. I have used an example with 2 antidepressants, fluoxetine and sertraline. I think I have to apologize, just like Mona did, that most of my examples are from the medical field. But I've tried to accustom a little bit to the education field, but I guess not very successfully. So anyway, what we aim to do is to see which one is more efficacious. So we design a systematic review, we get our studies, compute effect sizes. We end up with several randomized controlled trials with possibly contradictory results. And then we synthesize quantitatively all this evidence using meta-analysis. And we get an overall result that has increased power and precision. Well, meta-analysis, one of the limitations of meta-analysis is that it focuses on 2 interventions. For most problems, healthcare problems, but I also assume educational and social problems, there are lots of competing interventions, and we are interested to find out which one is the best. So staying in standard meta-analysis, I want to compare effectiveness of interventions for anxiety disorder, which is prevalent in children and adolescents. And there is a Cochrane systematic review published that evaluates the effectiveness of pharmacotherapy for anxiety disorder in children and adolescents. There is a more recent one with the same outcome, the same population, anxiety disorders, children and adolescents, but evaluate effectiveness of cognitive behavioral therapy, CBT. There is another one evaluating exercise, the same outcome, the same population. So I have 3 different reviews, the same problem, the same population, different interventions. And actually, it's not just 3 different interventions, it's 3 different classes of interventions. For example, pharmacotherapy, if you go to this review and you read the conclusions, it says that overall there is a benefit of drugs over placebo, but we need more research to find out which drugs are effective, because they are not all equal and not all of them beat placebo. If you go to the second one, it says that we need studies comparing individual CBT to group CBT and to family CBT. The third one says that we need studies that compare aerobic exercise to exercise that improves the strength. So actually, we can broaden the research question. And also, the first review says that we need to studies comparing pharmacotherapy to CBT. The second review says exactly the same thing. The third one says that exercise should be given as a supplementary treatment. So we should compare CBT plus exercise versus CBT alone, pharmacotherapy plus exercise versus pharmacotherapy alone. So actually, we can broaden a lot the research question. And I guess I should have pressed that before to, to show you that there are 3 different classes of interventions. So I will stay with the first, actually, review, the one focused in pharmacotherapy. There are 12 new generation antidepressants. These are the names: sertraline, reboxetine, and so on. What I'm interested in is not to find which ones beat placebo, but which one is the best, for whom and under what conditions. For example, they may be good for old people, not for young people. They may be good if you have severe depression, but not if you have mild depression, so on. If I focus just on standard meta-analysis, and actually several meta-analyses have been published comparing a pair of these interventions. So for example, there is one comparing mirtazapine to sertraline and said that mirtazapine is likely to be better, but we didn't get any significant results. The same with mirtazapine and paroxetine. Probably we didn't get significant results because we found 1, 2, or 3 studies comparing these two antidepressants, and we didn't have enough power to find a significant difference. There is another one saying that sertraline is better than fluoxetine. There is another one with a statistically significant result saying that venlafaxine is better than fluoxetine. Also, venlafaxine might be better than duloxetine. And there are at least 10 meta-analyses published each year comparing a pair of these interventions. So in the end, you have something like 50 meta-analyses. Can you make something out of it? Which one is the best? So the psychiatrist or the patient who wants to prescribe an antidepressant, or the patient, is actually left puzzled with all this chaotic information. And so these are some pairs. We found 2 studies comparing paroxetine to reboxetine, 1 study comparing duloxetine to mirtazapine, and so on. So we don't have enough power to estimate the relative effectiveness between 2 interventions. And actually, we didn't find any study comparing sertraline to duloxetine. So how are we going to compare the relative effectiveness between these 2? So that's where network meta-analysis comes into. There is a paper that actually compared all these 12 new generation antidepressants using network meta-analysis. And as you can see, they ended up with 117 studies. So instead of analyzing 1, 2, or 3 studies to find the relative effectiveness between 2 interventions, they have more than 100 studies, and they can estimate the relative effectiveness between any pair of interventions. So this is, so the question is actually how do they do that? How do they synthesize evidence from seemingly unrelated comparisons? This is a network plot. It usually accompanies any network meta-analysis. It's a bunch of nodes and edges. Nodes refer to treatments. Edges between 2 nodes refer to the fact that there have been studies comparing these 2 treatments. So for example, there is an edge from milnacipran to sertraline. That means that there are studies that have compared milnacipran to sertraline. So we have direct evidence about milnacipran and sertraline. There is an edge missing here from reboxetine to mirtazapine. That means that there are no studies. We didn't find any studies comparing reboxetine and mirtazapine. If you notice, this graph is connected. That means that I can go from any node to any other node. So information in this graph flows not only directly, but also indirectly. So for example, I cannot go directly from reboxetine to mirtazapine here, but I can go indirectly through fluoxetine. And I can find other indirect routes. I can go to sertraline, paroxetine, and then mirtazapine. And you can see that there are lots of different routes that you can get. If you notice, the size of the nodes do not have the same size. The size of the node is proportional. Actually, it's an option. Either you put it proportional to the number of studies involving this node, this treatment, or to the number of individuals that have been randomized to this group, to this treatment. So fluoxetine is the largest node. That means that most studies compare fluoxetine to something else. And actually, you can see that from fluoxetine, there are lots of edges going to other nodes. So do you have any questions so far? So let's see what, as I told you, you can go indirectly, you can from any node to any other node. So the indirect comparison, the indirect evidence is a key concept in network meta-analysis. So suppose that you have the Daltons, and you take one of them, the shortest one, to be the reference Dalton. And you know, now you know how much taller, you estimate how much taller is Jack to Joe, how much taller is William to Joe, and how much taller is Averell to Joe. Do you know how much taller is Averell to William? I guess yes, because it's just the difference. So that's the idea of indirect comparison. You just suppose that you take a reference drug, a reference treatment, you put its effectiveness to 0, you estimate how much more effective its other treatment is, and then you estimate indirectly the differences between any two treatments, any two individuals in this case. So suppose that we have treatments A, B, and C. And I have A-B studies, studies comparing A and B. And I also have A-C studies, studies comparing A and C. Can I estimate indirectly the relative effectiveness between B and C? Yes. It's the same with the height. I know how much better is B to A, how much better is C to A, or worse. So I know how much better or worse is C to B. So the algebra, and I think this is the only equations that you're going to see, it's just simply vector geometry. I estimate the relative effectiveness between A and B and A and C. I subtract them, and I get an indirect estimate from B and C. AC and AB comparison studies are independent, so the variance is just the sum of the variances. So I have an indirect estimate and its variance. And that means that I can estimate a confidence interval. So let's say that I have a placebo treatment, I have a SSRI, this is a class of drugs, and cognitive behavioral therapies. I know that I measure depression, so negative numbers mean that SSRI is better compared to placebo. Depression is decreased. CBT is better than placebo. You have the numbers. Actually, you also have a confidence interval for each, from each direct estimate. Can you estimate how much better is CBT compared to SSRI? What would that number be? Anyone help me? So I need to go from, oh, sorry? Yeah, 15. Yeah, I need to go from minus 0.19 to minus 0.34. So it's just minus 0.15. I can estimate the variance because I have the standard errors from its direct comparison. So I can estimate the variance of the indirect estimate, and I can estimate a 95% confidence interval. That tells me that the indirect estimate ranges from minus 0.26 to minus 0.04. So is CBD better than SSRI? I don't have any direct evidence. I only have the indirect evidence. I have a confidence interval that does not include 0. So CBT seems to be better than SSRI. Was that clear? So once again, we have A, B, and C treatments. A and B are compared to C. That means that I can get an indirect estimate. I use the dotted line. But it could be the case that I have also studies comparing A and B. So I have also a direct evidence. And network meta-analysis synthesizes both these two sources of evidence, and we get a network meta-analysis effect estimate. So I may have both direct and indirect evidence. And actually, back in my network plot, suppose that I want to estimate the relative effectiveness between fluoxetine and sertraline. That was my original question. And I have studies comparing these two interventions. So I have direct evidence. I also have indirect evidence. There are lots of routes that I can take to go from one node to another. So network meta-analysis will synthesize both direct and indirect evidence. So as I told you before, I don't have studies comparing sertraline and duloxetine. So here I don't have direct evidence, I only have indirect evidence. For example, both of them are compared to milnacipran, and I use that to get an estimate for the relative effectiveness. I have studies comparing paroxetine to reboxetine, but both of them are compared to fluvoxamine, so I can get both direct and indirect evidence and synthesize it. So network meta-analysis allows me to analyze all treatments simultaneously, to use both direct and indirect evidence, to estimate the relative effectiveness between treatments that have never been compared, like sertraline and duloxetine. And also, one of the standard outputs is a ranking of the treatments. We can compute the probability of a treatment being the best, the second best, the third best, and so on. So for example, in this example, mirtazapine has a 54% probability of being the best, followed by escitalopram, then venlafaxine, and so on. So I can get a ranking of the treatments and to see which one is the most effective. Is that clear so far? Okay, so this is a summary of what I just said. So we synthesize direct and indirect evidence, we get a ranking of the interventions, we evaluate the effectiveness of treatments that have never been compared. I can also include in the analysis studies with more than 2 treatments. And all these benefits are well recognized, but unfortunately there are also some limitations. And network meta-analysis is not yet an established practice. It's mathematically more complex. Software is not that user-friendly, although it has improved a lot. But the major drawback is the observational nature of indirect evidence. So if I have a study and I randomize participants to go to the treatment group or the control group, then I estimate an effect size, which is actually a function of control and treatment group. And if the effect size tells me that there are differences between these 2 groups, I know that the group is responsible. Here, the indirect evidence takes AB studies and AC studies and estimates a difference between AB and AC studies. But studies are not randomized, comparisons are not randomized to studies. So it could be the case that the AB studies have young populations and the AC studies have older populations. If age is a moderator, is an effect modifier, that would have an impact on the results. Was that clear? So usually we identify a priori some possible effect modifiers that modify the effect. And we see if the distribution is the same across comparisons, across AB studies and across AC studies. And we see if they are different in patient characteristics in AB studies and AC studies. Well, I'll describe this limitation in more detail in the next slides. So actually, any model is based on some assumptions. If the assumptions are valid, then the model is good. And the main assumption of network meta-analysis is that of transitivity. That means that I can learn about B and C via A. And it's an untestable assumption, but can be evaluated clinically and epidemiologically. So if I know what modifies the effect, I'm just looking at the distribution of that variable in A, B, and AC studies. This transitivity assumption implies the intermediate treatment, for example, A, to be equivalent when it is in AB studies and in AC studies. For example, in AB studies, A could be a pill. In AC studies, it could be an injection. So are they equivalent? I don't know, maybe a placebo pill is better than a placebo injection or vice versa. So the intermediate treatment should be equivalent in A, B, and AC studies. Also, the studies that contribute to the indirect comparison should not differ in important ways. Like if age is an effect modifier, I want the age of participants to have a similar distribution in AB studies and AC studies. So I will describe now the second bullet point. Suppose that I have AB studies and AC studies, and A is a pill given in different doses. But the average dose in AB studies is the same in AC, with the average dose in AC studies. Would the transitivity hold then? So I know that just across studies, I expect the dose to change, to differ across studies. But here, across comparisons, the average dose is the same. So I wouldn't expect that to influence the results, to bias the results. So in this case, I can take A to B, the same treatment, identical. And the transitivity probably holds. Here I may have a treatment A if I compare CBT to antidepressants. I don't know if a pharmacological placebo is the same with a non-pharmacological placebo. So maybe it doesn't hold. Was that point clear? Yeah.
You might be a question about the first one, like if the dose response was not sort of linear, you know, that it cured everybody at the top end and only half the people at the bottom. But you know,
Well, with doses, I think it's always a problem. Either you use the dose as a moderator, as a different treatment, or you just group them together. But what we are interested in here is just not about if the effect is linear or whatever, but if the transitivity refers only to the expected value, the average of the dose. I don't know if that answered you. Huh?
disagree, but
So let's see another example. We have three treatments, A, B, and C. In the vertical axis, I have the effectiveness of the treatments. In the horizontal, it's the proportion of women in the studies. So if I want to get an indirect estimate about B and C, I just compute the differences of C, A, and BA, and I subtract them, and I get the difference. Suppose now that the effectiveness of treatment A is not the same, but across all studies, but depends on the representation of women in the sample, in the study. So the more women we have in a study, the more effective treatment A is. So when I compare C to A, the effectiveness of C compared to A decreases as the proportion of women increases. The same with B. But here I'm interested in the indirect estimate between B and C. Would that change? Would that be a problem?
Between B and C?
Yeah, no, because the difference is the same at any point. So in this case, the effectiveness of A depends on gender, but I have the same distribution of representation of women in AB and in AC studies, and that does not affect the results. So in this example, still intervention A, the effectiveness of A depends on the proportion of women. Would that be a problem here? I have AC studies that have, on average, they have a smaller representation of women. And I have BA studies that have more women than AC studies. So an indirect estimate would be biased. And can you tell me which treatment the bias would favor? Look at the difference between C and A. It's quite large. So C appears to be very effective. But this is probably because I have the studies that compare A and C have a small representation of women. So I would get a biased result and bias would favor treatment C. So I would get the same difference, but it's not real, actually. And usually it's difficult to defend transitivity, the main assumption, when we have older and newer treatments. Because if we have, if B is an old treatment, and it's compared, it's included in studies conducted 20 years ago, the studies are probably of poor methodological quality. They show exaggerated results. And I compare them to AC studies that are new, and they don't show such exaggerated results. So suppose now again that I have A, B, and C. AB studies are in adolescents, AC studies are in children. So would transitivity hold here? So the main question is age an effect modifier? So the effectiveness depends on age. I have some other examples here where I think the most common is publication date. When you have old studies and new studies, the indirect estimates may not hold. Some treatments are very effective in developed or in developing countries, and not in developing or the opposite. Also, the baseline risk is some treatments are very effective in populations that are at high risk. Any questions so far? Is that supposed to be a good thing? Or a bad thing? Huh? It's a bad thing. So we cannot actually test empirically transitivity, but there is a statistical counterpart called consistency. And the consistency assumption states that direct and indirect evidence should be in agreement. So I estimate the direct, I get the direct estimate, and indirect, and I just compare them. If they are equal, then we have consistency and probably transitivity holds. So we check the consistency assumption wherever we have direct and indirect evidence. So the dotted line is the indirect evidence, the solid, the direct, and the assumption, the hypothesis that we test is that indirect estimates are equal to direct estimates. So I have an example here. It's placebo, exercise, SSRI, and CBT. How many indirect estimates can I get here? In order to get an indirect estimate, you need a closed loop. So I need a study that is compared, if I have A, B, and C, and I want to get an indirect estimate from B and C, I need both of them to be compared to A. So I need a closed loop. Can I get an indirect estimate for exercise versus SSRI? Yeah, they are both compared to placebo. Can I get an indirect estimate exercise versus CBT? Yeah. An indirect estimate SSRI versus CBT? Yeah, all of them are compared to placebo. The consistency assumption compares the indirect estimate to the direct one. Can I test the consistency assumption in exercise versus SSRI? I get an indirect estimate. There is no direct evidence. So I cannot estimate consistency there. So I just estimate consistency in closed loops. So in this one. And I admit this was a terrible. This one I did it myself. So I can only estimate consistency in that loop. Can I can I explore transitivity in exercise versus placebo? Consistency refers to closed loops, but transitivity, I just want to see if the distribution of effect modifiers is the same across comparisons. So I can get the exercise versus placebo comparison and see if I believe that age is an effect modifier, see if the distribution of age is the same in that comparison, in that, and so on. So I can explore transitivity everywhere and consistency only in closed loops. And from network meta-analysis, I get results. It's like the example I showed you with the Daltons. I take placebo to be the reference treatment, and the results would be each therapy versus each intervention versus placebo. So estimating the model, I just choose a reference treatment, placebo. I choose some basic parameters, the difference of the rest of interventions compared to placebo. And from that point on, I can estimate all the other, the relative effectiveness between all the other pairs of interventions because they are just functions of these basic parameters. Any questions? Yeah. Okay, so for each closed loop, we estimate what we call an inconsistency factor. If we have, for the closed loop, we have the indirect evidence of SSRI versus CBT. We have also the direct evidence. We have the variance of the indirect estimate and the direct estimate. And we just subtract it to find what we call the inconsistency factor. And we also use take absolute values because we are not interested in the direction of consistency. And then we estimate the variance of this inconsistency factor, just the sum of the variances of direct and indirect evidence. And we have a z-test to test the hypothesis that the inconsistency factor is 0. Also, we can create a 95% confidence interval. So in this example, the difference between direct and indirect evidence lies from minus 0.05 to 0.43. So it includes 0. That means that direct and indirect evidence are in agreement. So I do that for every closed loop in the network. Was that clear? Yeah, with a lot of interventions, it's a lot of tests. And you have problems of multiple testing, and there are also global tests for inconsistency.
There is.
Yeah, there is, and also in each loop separately. Yeah. So we have with my colleagues, we have developed a series of Stata routines to summarize results from network meta-analysis. I'll show you some of them. Well, the most important plot is the network plot that tells you how information flows in the network, directly and indirectly. So you can use weighting schemes like the one I showed you before. You can adjust the size of the node to be proportional to the number of studies that involve this treatment. And so actually here you can see that most treatments involve placebo. You can also see from the active treatments, the most frequent is olanzapine. The thickness of the edges is proportional to the number of studies that have this comparison. So there are lots of placebo-controlled trials. You can see that all the edges going from placebo to the other treatments are very thick. That means that there are lots of trials that have been conducted comparing placebo to one of these treatments. So olanzapine is the most frequent active comparator. And also you can change colors in the edges depending on various baseline characteristics. So what we have done here is that we evaluated studies in each comparison in terms of blinding, if they were at high risk of blinding, low risk of blinding, or unclear. And yellow means unclear, green is low, red, we don't have any red, is high. So you can see, for example, that the placebo-controlled trials are yellow. That means that there are at unclear risk of bias. The green lines between some active treatments, they give you information that these comparisons, these studies, are at low risk of bias. So if I want to estimate the inconsistency in a loop involving a green line and two yellow lines, would transitivity hold? Well, I don't know actually, it's an untestable assumption, but you have studies that are at low, unclear risk of bias, probably high risk of bias. You have studies that are at low risk of bias. So the ones that are the ones with the yellow lines may show exaggerated results. Did that make any sense? You have a loop, but not all. Think of the loop olanzapine going to haloperidol and back to placebo. You want the distribution of effect modifiers to be the same across comparisons. If blinding is an effect modifier, it's not the same. So transitivity may not hold. So this is a command in Stata, network plot. We have another command that I'll show you that gives you information about how much each direct comparison contributes to the entire network, and also how much is the contribution of the indirect evidence. Suppose that I have this network. These are the 4 direct comparisons. So I have placebo versus exercise, placebo versus CBT, placebo versus SSRI, and CBT versus SSRI. And these are all the estimates that I get from network meta-analysis, because I get estimates for the direct and the indirect comparisons. If you look at this comparison, placebo exercise, there is no indirect evidence here, actually. Because all the information for the relative effectiveness of exercise versus placebo comes from that studies. So I would expect here to have 100%. So the placebo versus exercise comparison has all the information about the placebo versus exercise effect. Similarly, I can compute the rest of percentages. So the network meta-analysis estimate for placebo versus CBT gets 68% of the information from placebo versus CBT, and the rest from the other 2 direct comparisons. And I can also see where do the indirect estimates get the information from. So exercise versus CBT, there are no direct studies comparing these two. And I know that they take almost 46% from that comparison, 37% from that, and very little from the other two. And also, I know how much each direct comparison contributes to the network. So most of the information comes from here. Was that clear? So we have another command called the if plot, inconsistency factor plot, that estimates inconsistency factors from all closed loops of evidence. and actually gives you a graph. It plots all these inconsistency factors. So suppose that I have this network. How many inconsistency factors are there? How many loops do I have? I have ABD for sure, ACD. I also have ABCD, but because they are not independent, because the two smaller loops, if you put them together, you get the bigger one. Actually, I need to estimate two inconsistency factors. So actually, I have two triangles. And I estimate the direct effect of B versus D and C versus D. I estimate the indirect effect from the other studies, and I test the hypothesis. This is the inconsistency factor, and I test the hypothesis that it is equal to 0. And I do that for all loops. So in the network that I showed you before, as you said, you have many inconsistency factors. And normally you test if inconsistency factor is equal to 0. But here the effect size is the logarithm of the odds ratio, so I took the exponent of it. So I test if it is equal to 1 or not. And if you look closely at this, you get only one inconsistency. But with all these loops, you have problems of multiple testing, and it's probable that you will find a significant result by chance. So I think this is a very good picture. I think this network is consistent. Any questions? No. So also we can, network meta-analysis, as I told you, allows us to rank the treatments. And there is I will not give much details on how ranking is computed, but we estimate for each treatment the probability of assuming each possible rank. So if I have 3 treatments, I will go to the first one, and I will compute the probability that this is the best, the second best, and the third best. So we can estimate the probabilities of being the best, but until recently that was routinely done. But this ignores information, actually it ignores uncertainty in ranking. And we have developed measures that take into account the probability of being the second best, third best, and so on. So probability that take into account the entire distribution of the ranking probabilities. So one of them is the rankogram. So I have here 7 antidepressants. In the horizontal axis, I have the ranks, and the probabilities are in the vertical axis. So you can see, for example, that this treatment here has a high probability, a large probability of being the best, like 0.50 or something like that, a large probability of being the second best, and it goes to 0 very quickly. So probably it's the best. You can see that this treatment is probably the 6th. And this treatment is probably the 7th, the last one. And so on. This is the second, I think the third, 4th, and 5th. Is the rankogram clear? So instead of just of the rankograms, we can plot the entire cumulative probability, ranking probability. So this is actually, in the horizontal axis, it's again the rank, and the vertical is the probability. But here, this is the probability, for example, here, you get a probability of 0.6. That means that there is a 60% chance that this treatment is either first, second, or third. So actually here we check which treatment goes faster to 1. So this goes very fast to 1. And we can compute the area under this curve. And the larger the area, the better the treatment. So this one that goes very fast to 1 has the largest area. Was that clear? We call this SUCRA, which means, I forgot what it means. Oh, surface under the cumulative ranking area. Oh, no, doesn't make sense. Surface under the cumulative ranking curve, I think it is. So actually, network meta-analysis allows you also to rank treatments in terms of many outcomes. So for example, you are interested in acceptability, in efficacy, and also acceptability, safety. So I have 2 different outcomes. I can rank them. I can compute SUCRA values for each treatment. So you can see that aripiprazole actually it's quite effective, but not very good in terms of acceptability, how patients accept it actually. And I can compute the rank in both outcomes and then plot it. So if, for example, risperidone, these are the SUCRA values. It has a very large SUCRA value for efficacy and also a very large SUCRA value for acceptability. You can see some other drugs like paliperidone. It has a large value for acceptability, but not so large for efficacy. So you can get a rough idea of ranking with more than 1 outcomes. Yeah. And well, this is our website where we give we have directions on how to do a network meta-analysis, and we have and how to use all these commands, how to put your data, do the analysis step by step. And this is the paper that we describe these commands that I just showed you. And I just have some references here. Ian White has developed a MV meta in Stata, which is actually now he's making the new version of it, which would be very easy and straightforward to use. Sorry?
What did you say there?
I'm saying he has developed a command called MV meta in Stata, and now he's working on the new version, which is very user friendly, and it's pretty straightforward. Just some references, and I didn't check time, but I'm happy to get any questions.